What if the most dangerous earthquake warning in California was not the earthquake that destroyed a city, but the tiny earthquake that almost nobody noticed? A magnitude 4.2 earthquake is the kind of event most people forget before their coffee gets cold. A few windows shake, a few phones receive an alert. A few people look around and ask, "Was that an earthquake?" Then life continues. But deep beneath the mountains of Southern California, something happened that made scientists look twice. Because this earthquake did not happen anywhere. It happened at a place where two of North America's most important fault systems meet. A hidden intersection, a geological crossroads. A place where the massive San Andreas Fault collides with the lesser-known Garlock Fault. And the question is not, how big was this earthquake? The question is, why did the Earth choose this exact place to move? Because sometimes the smallest movements reveal the biggest problems. On a satellite image, the region looks almost ordinary. Golden mountains, dry valleys, a highway cutting through the landscape. Nothing about it suggests that millions of tons of rock beneath the surface are constantly fighting against each other. But zoom in, the landscape begins to tell another story. The mountain ridges are not random. The valleys are not random. The curves of the terrain are scars created by forces moving slower than human civilization can observe. This is where California's underground battle is happening. Near Frazier Park, close to Tejon Pass, Interstate 5 crosses one of the most complicated sections of the entire California fault system. Above ground, vehicles move through the mountains every day. Below ground, the planet is storing energy, and every year that passes without a major rupture does not mean the danger disappears. IT means the system continues loading. The earthquake itself was small, but its location was unusual. The shaking occurred near the junction where the San Andreas and Garlock faults interact. Two faults, two different directions of movement, two different sources of tension. The San Andreas is famous. It is California's legendary fault line, a nearly 800-mile scar where the Pacific Plate slides past the North American Plate. For more than a century, scientists have studied it because it has the potential to produce enormous earthquakes. But the part most people miss is this. The San Andreas is not dangerous only because it is large. It is dangerous because of where it connects with everything else. And one of those connections is the Garlock Fault. The Garlock Fault does not have the same reputation. It does not appear in movies. It does not dominate headlines. Most people living near California have never heard its name. But underground, the Garlock represents one of the most important pieces of the puzzle. It stretches across the Mojave Desert and connects with the San Andreas system. Unlike the San Andreas, which moves mainly sideways in one direction, the Garlock moves in the opposite horizontal direction. Two massive geological forces pushing against each other. And where those forces meet, the ground becomes complicated. The problem is not simply movement. The problem is resistance. Imagine bending a piece of metal at. The metal absorbs the pressure. It looks stable, but the energy is still there. The Earth behaves in a similar way. The plates beneath California are constantly moving, only a few centimeters each year, about the speed your fingernails grow, but over decades and centuries. Those tiny movements create enormous pressure. The rocks lock together. They bend. They store energy. Then eventually something gives. This is called elastic rebound, and it is the basic mechanism behind major earthquakes. The ground does not suddenly become dangerous. It becomes dangerous slowly, quietly. Over generations, the San Andreas near this region has another complication, a massive curve known as the Big Bend. On a map, it looks like a simple change in direction, but underground, it changes everything. A straight fault can slide more easily. A curved fault creates friction and compression. The rocks are forced together. They push upward, And that pressure created the mountains surrounding Los Angeles. The mountains are not just scenery. They are evidence that the Earth has been fighting itself here for millions of years. The landscape is a record of stored energy. But here is where the story becomes more complicated. Because this earthquake did not happen in a quiet system. 6 years earlier, another earthquake changed the pressure map beneath California. In 2019, near Ridgecrest in the Mojave Desert, the ground suddenly ruptured. First came a magnitude 6.4 earthquake. Then 1 day later, a magnitude 7.1 earthquake struck. The desert floor split open, roads were damaged. The rupture lines were visible from space. But the most important consequence was not what happened above ground. It was what happened below. When a major earthquake occurs, it does not simply release energy, it redistributes it. The Earth is connected. A fault that moves in one location can increase pressure somewhere else. Scientists call this Coulomb stress transfer. The idea is simple. One earthquake can push another fault closer to failure. After Ridgecrest, researchers found that stress increased on sections of the Garlock Fault. The exact numbers remain part of ongoing scientific discussion, but the broader conclusion was clear. The earthquake changed the mechanical environment around nearby faults. And then something unusual happened. The Garlock began showing signs of movement. Satellite measurements detected slow creeping along parts of the fault. A fault that had remained quiet for a very long time was no longer behaving exactly the same way. But this creates one of the biggest misunderstandings about earthquakes. People often ask, does this mean the big earthquake is coming? The honest answer is, nobody knows. And that uncertainty is what makes earthquake science so difficult. A small earthquake can be a warning, or it can simply be a small earthquake. Most smaller earthquakes do not become the beginning of a larger disaster, but the location matters. A small movement in an empty desert is one thing. A small movement at a major fault junction is something scientists examine much more carefully, because the question changes. It is no longer about the size of the earthquake. It becomes about what the earthquake reveals about the system underneath. And that system has a long memory. In 1857, the Fort Tejon earthquake struck along the southern San Andreas. Estimated magnitude, around 7.9. The rupture stretched hundreds of miles. The ground shifted dramatically. At places like Wallace Creek, the landscape still records that moment. A stream channel sits offset by the movement of the fault. A scar frozen in time. A reminder that the ground beneath California has moved before, and it will move again. The bigger picture becomes even more concerning when you look at the geography. This fault junction is not located in an isolated wilderness. It sits beneath one of California's critical transportation and infrastructure corridors. Interstate 5 crosses this region. The California Aqueduct crosses. This region, energy infrastructure crosses this region. Water, fuel, electricity, transportation. The systems that keep Southern California functioning all pass through a landscape shaped by ancient earthquakes. The hidden danger is not only the shaking. It is the possibility that a geological event could disrupt the networks built on top of it. And this reveals the first major contradiction of this story. Everyone sees an earthquake, but the real issue is not the earthquake. It is the system behind it. Because modern disasters are rarely caused by one event alone. They happen when a powerful event meets a vulnerable system. A fault creates the energy. Infrastructure determines the consequences. Technology measures the danger. Politics decides how prepared society becomes. The earthquake is only the beginning of the story. Today, California has one of the most advanced earthquake monitoring networks on Earth. Thousands of sensors watch the ground constantly. GPS stations measure movement down to millimeters. Radar satellites track changes in the landscape from space. For the first time in human history, people can watch the planet breathe. But here is the problem. Seeing the Earth move does not mean controlling when it breaks. Scientists can measure stress. They can identify dangerous zones. They can improve warnings, but they still cannot predict the exact day and hour of a major earthquake. And that leaves California facing an uncomfortable reality. The most important question is not, can we stop the earthquake? We cannot. The real question is, can we understand the warning signs before the earth decides to move again? Because beneath the mountains near Tejon Pass, two giant faults are still locked together. And the small earthquake that woke everyone up may not have been the disaster. It may have been the reminder. The biggest mistake people make when studying earthquakes is looking only at the moment the ground breaks. The shaking, the collapsing buildings, the dramatic images. But the real battle begins long before the surface moves. Deep underground, the earth is constantly negotiating between pressure and resistance. And at the San Andreas-Fagerloch Junction, that hidden battle may be more important than the earthquake itself. Because everyone thinks this story is about a magnitude 4.2 earthquake. But the real story is about a system under pressure. A system where geology, infrastructure, technology, and human decisions are all connected. Look at California from above. A satellite image does not show fear. It shows patterns. A thin line of cities stretching along the coast. A massive transportation network, crossing mountains and deserts. A web of pipelines and power lines, feeding millions of people. And underneath all of it, a network of faults that does not care about borders, highways, or human schedules. The Earth follows its own timeline. That creates the first major lesson. A fault does not need to destroy something to change the future. Sometimes the most important events are the ones that force humans to rethink what they believe they understand. Everyone knows about the San Andreas, but the part most people miss is that earthquakes are not controlled by individual faults. They are controlled by systems. The San Andreas is not a single crack. It is part of a much larger mechanical network, the Garlock, the Walker Lane. The faults beneath the Sierra Nevada, the offshore systems near Northern California, all of them are connected by the movement of the Pacific Plate and the North American Plate. The question is no longer which fault will break. The deeper question becomes, how does one moving piece change the behavior of everything around it? This is why the 2019 Ridgecrest earthquake matters. From the surface, it looked like a desert earthquake, a remote event far from major cities. But underground, it was something different. It was a stress redistribution event, a reminder that the Earth does not divide itself into neat sections. When one fault moves, another fault can feel the consequences. A battlefield commander would understand this immediately. One unit moves, the entire front line changes. The same principle applies underground. The battlefield is just slower and invisible. This is the hidden battlefield of earthquakes, not the shaking, not the cracks in the ground. The hidden battlefield is information. Scientists are fighting a war against uncertainty. Every GPS station, every satellite image, every seismic sensor, every computer model, they are all attempts to answer one impossible question. What is the Earth preparing to do next? And this changes how we think about technology. Technology does not eliminate danger. It changes the relationship between humans and danger. A warning system cannot stop an earthquake, but a 10-second warning can stop a train. It can shut down machinery. It can give someone time to move away from a dangerous location. The advantage is not preventing the disaster. The advantage is reducing the consequences. But here is the problem. Modern society has become incredibly efficient, and efficiency creates vulnerability. Southern California depends on systems that move enormous amounts of water, energy, and transportation through narrow corridors. The same geography that makes these systems practical also creates risk. The California Aqueduct carries water across the state. Interstate 5 connects major population centers. Energy networks cross fault zones because geography leaves few alternatives. The invisible battlefield is not only beneath the ground, it is above it. It is the relationship between natural forces and human infrastructure. This is why major earthquakes are not simply geological events. They are strategic events. A large earthquake in California would not only damage buildings, it could disrupt logistics, water distribution, fuel movement, emergency response, economic activity. The consequences would spread through systems that people rarely notice until they stop working. A modern city depends on thousands of invisible connections. The failure of one connection can create pressure somewhere else, just like faults underground. And this reveals another contradiction. The places humans build are often the same places the earth creates. Rivers, coasts, mountain passes, transportation corridors, the same landscapes that support civilization are shaped by geological forces. Humans build on the battlefield, then spend generations trying to understand it. The lesson here is not that California is doomed. That is the wrong conclusion. The lesson is that preparation is a form of power. Military strategists understand this. The strongest force is not always the one with the biggest weapon. It is the one that understands the environment better. The same principle applies to natural disasters. A society that understands risk can absorb shocks better. A society that ignores risk becomes surprised by predictable problems. No, look beyond California. Because this story represents a much larger change in how humanity thinks about disasters. For most of history, earthquakes were viewed as sudden acts of nature, something that happened without warning. Today, humanity sees something different. We see systems, patterns, connections. We understand that disasters emerge from interactions between natural forces and human choices. The earthquake is the trigger. The vulnerability determines the outcome. And this is where the story connects to geopolitics and national strategy. Countries around the world are beginning to recognize that resilience is a strategic advantage. Military planners study supply chains. Energy companies study infrastructure risks. Governments study disaster response. Because a crisis does not have to be caused by an enemy to create national consequences. A damaged port, a broken power network, a disrupted transportation route. These can create effects similar to strategic attacks. The battlefield of the future, it is where systems survive. But the biggest question remains unanswered. What does this small earthquake actually mean? Could it be a warning before a larger event? Possibly, could it simply be a normal release of energy inside a complex fault system? Also possible, the science does not allow certainty, and that uncertainty is exactly why monitoring matters. The goal is not predicting the impossible. The goal is understanding probabilities, reducing surprises, building resilience before the moment arrives. Because earthquakes do not announce themselves. They do not send messages. They do not provide a countdown. They simply wait until the balance between pressure and resistance changes. And when it changes, everything built on top of the earth must respond. The question is no longer, can humanity stop the next major earthquake? The real question is, can humanity build systems strong enough to survive a world that is constantly moving beneath our feet? Because the future of disaster response will not be decided only by the strength of the earthquake. It will be decided by the strength of the technology, the infrastructure, the preparation, the decisions made before the ground starts shaking. So the question for you is, do you think future disasters will be defined more by the power of nature or by how prepared human systems are to absorb the impact?